Hello. So this is the new title. Can people still hear me? Okay. This is the new title, which is just a slight modification of the old one. First, I just want to say what a sense of privilege I have to be here, and particularly on an occasion when we're saying farewell to one of the true giants of the industry. So before I this talk is largely philosophical in nature, and it's partly along the lines of giving similar talks in the past, but I think that even though the theme is a little bit similar to what I've said in the past, the need for kind of putting some philosophical underpinnings into what we're doing as modelling, I find even more urgent, particularly in light of the arising number of guidelines that are telling us how to model. Very few really are based on any scientific principle, and I just want to address that issue. But before I do, just to mention a couple of new things that are in the PEST suite, and why I'm putting them in, because they are put in to support kind of the view that I think that models should take in the decision-making process. In the last year or so, pilot points has been a pivot of the development area where we're trying to use parameterization devices that are somewhat geologically realistic, but can be adjusted during the history matching process. As in most modelling contexts, some kind of history matching is required, and pilot points seems to be a tool that can at least rise to somewhat to the occasion. So now we've got better interpolation methods from pilot points to model grids and meshes. We can have spatially varying anisotropy for both the interpolation, the regularization, and the random field generation. And I know that spatially varying variograms is kind of contradiction in terms, but trying to get away from the classical two-point statistical method of parameterizing using pilot points and much more flexible and much more representative of geological conditions. Better improved 3D pilot points for mining and deep high temperature geothermal applications. We've got movable faults, which can also have pilot points along fault planes, and the fault planes can move and intersect. And we've the ability now to have surrogate models, because something I'll talk about in the next half hour is that complex models that we often use make it virtually impossible to live up to the only promises that complex models can make, quantification of uncertainty. We're not going to be able to do this unless we can use maybe simpler models to do the sensitivities on which history matching and uncertainty analysis depends. Got a basic interface to SGEMS, that's public domain geostatistical software, and improved linear analysis for looking at the cost of simplification, the man-made uncertainty that we incur through using a simpler model or a defective model, and recognising that all models are defective. This is somewhat important. So the rationale behind that is to give PEST, to give models through the use of PEST a better role in the decision-making process. And that's the kind of modelling context in which I normally work, where models are used to aid in the decision-making context. And I think in doing that, we're not doing a real good job as an industry in using models properly to help the decision-making context, because even though it all sounds simple, I think some very basic factors have been forgotten when we apply models, and I just want to cover that ground now. So the common approach to modelling, there's a problem somewhere in a piece of ground, a proposal is requested, and it's a funny thing, I was talking to people the other day, when you see proposals written by consultants, the words precision, accuracy, is just every page has got that word once or twice. So that the idea, because obviously the client wants a model that's going to be precise and accurate. When it comes to the report that's written at the end of the job, words that are singularly absent from the consultant's report are precision, accuracy. These are replaced with words like suggest or possible, which actually is much more in harmony with what a model can deliver, but it's amazing how the language changes between the promise and the deliverable. So anyway, the contract is signed, the deliverable is then agreed upon. A set of standards are adopted as to be the metric by which the model can be judged, and as I want to point out, most of these standards are firmly rooted in fairy tales. And the crystal ball is designed and built, and then if we're lucky, a little bit of post-calibration sensitivity analysis will be done just to pay some respect for the fact that maybe, just maybe, the numbers that we've just produced with that model may be wrong. A little bit, possibly. And along the way in building this crystal ball, a lot of decisions have to be made. How complex it should be and how well it should be calibrated, things like that. And one of the problems is I think a lot of these decisions are made not in a proper framework. There needs to be a reference point and a metric through which we can measure up each of these decisions. And normally that metric is absent, and these decisions are made more for the sake of appearances and for the sake of science, and I think that needs to be addressed. People are not game not to be over-complex because someone might criticise them if something precious is left out of the model, which actually may be more of a millstone around the model's neck than an aid to the model's ability to assist the decision-making process. So, I just want to start at the problem and work backwards. So making decisions. There's a lot of theory about that, and I think this is one of the best papers about that. And when making decisions, normally it's done in the context we want to do something and we want to avoid a bad thing happening. And the role of the model then is to tell us, if we do this, can we assess where we lie statistically in relation to that bad thing? Or can we test the hypothesis that that bad thing can happen, and then can we adopt a management, a way of managing the environment, or digging the hole or the tunnel or whatever, such that we can provide some kind of guarantee that that bad thing won't happen. And that can be as complicated as we like. For example, if we decide we want to do this and we can't reject the hypothesis that that bad thing will happen, it may be that what we want to do may have to be modified. For example, we will guarantee that if a certain monitoring threshold is crossed in monitoring wells, then we will change our behaviour, and on that basis of that management strategy, provide the guarantee that a bad thing won't happen. But in the end, it does come back to providing that guarantee to the investors that the investment won't go sour, to the society that environmental damage won't be done, that there's one or a number of bad things won't happen, and the model's place in the decision-making framework is to assess and hopefully provide that guarantee. Now, as it happens, that's perfectly aligned with the scientific method, and the phrase scientific method and modelling hardly ever appear in the same sentence. And because we're probably, the way models are looked upon, especially by those who pay for models, is more aligned with the sort of philosophy you'd see in a Harry Potter novel than what you'd see in a scientific textbook as a means of implementing the scientific method. And what is the scientific method? Well, as espoused by the philosophers of the scientific method like Karl Popper, it says that knowledge is asymmetric, that we can test hypotheses, we may be able to reject them, but we can never accept a hypothesis. That that knowledge itself, and particularly scientific knowledge, is the process of testing and seeing if we can reject hypotheses. Those there may be more than one hypothesis still retained. And in our case, if we're going to actually implement the scientific method, then our scientific instrument, blunt as it is the environmental model. So, and as it happens, that the scientific method then is perfectly aligned with the requirements of the decision-making process. The need to test a hypothesis, in this case, the bad thing that managers don't want to happen, and see if that can be rejected. So there should be no problem at all in aligning what we do as modelers with the requirements of the decision-making process and with the demands to which we should all adhere, the demands of the scientific method. So, and why then, if we are going to look at modelling in that framework, how can then we use modelling as a scientific instrument to test and reject hypotheses? Well, in the end, if we're going to reject a hypothesis that a bad thing will happen, there's two things that will allow us to reject that hypothesis. And that is, if the happening of that bad thing is demonstrably incompatible with one of two things. Expert knowledge, as it now stands, or B, the historical behaviour of the system. And if this bad thing can be demonstrated to be incompatible with those, then the hypothesis can be rejected. So I'm just trying to build a chain of logic here that will allow us to put some of the important decisions we have to make in modelling into some kind of context, starting with the scientific method, and what other place is there to start, really. So, why then is a model able to do, a fairly unique position to do this? Because those two things that we have to test compatibility with, it is kind of has receptacles for that information. The model can provide the receptacles, and I think it's probably just as helpful to look as a model, not as a simulator, though it is, but in a decision-making context, as a receptacle for the two types of information by which we can assess and maybe reject hypotheses that bad things will happen. Now, what often is, but should not necessarily be asked by a model, is all these things, and they're all in the standards and guidelines we're often told if you don't live up to, you won't get the job. But in the end, all these are just means to an end. The end is to test and see if we can reject hypotheses that bad things will happen. So, if we're going to accept that and follow that chain of logic and accept that proposal that we should implement accept the novel idea that we should implement the scientific method, and it follows, and accept the asymmetric, the stochastic nature of knowledge, then we should accept that a fundamental principle is that, in spite of what's often said in proposals and in requests for proposals, a model will never tell us what will happen in the future. A model has the capacity to tell us what will not happen in the future, but we should never ask a model to do anything other than that. To say what will happen, cross, no. To say what will not happen, it does have the ability to do that if used in the right way as a scientific instrument in the decision-making context. But rarely, if ever, is the role of the model in the decision-making context stated in what is a way that is, when you come to think of it, so blatantly obvious, but always unstated. That aura of the crystal ball hangs around just about every model ever built, firmly rooted in wishful thinking. So, and if we're going to say, well, we've got to do things right, again in harmony with the asymmetric nature of knowledge, we've got to first define what is wrong. So we've got to first define failure. And failure then, if we're going to adopt this line of thought about how to use modelling in the decision-making context, failure is if we test a hypothesis and we say that a bad thing won't happen, and it does, then we failed. This then, that's the type 2 statistical error, false rejection of a hypothesis. So this then provides a kind of a metric, again rooted in the scientific method, of how, when we come to make all the decisions we need to make in building a model, this is the thing we have to avoid at all costs, is when we tell our client, tell society it won't happen, and it actually can. And then this then becomes the metric by which we judge all the decisions we make in building a model. So this means that uncertainty analysis and hypothesis testing have to be firmly at the heart of model usage. And if we're going to talk about that, we've got to talk about Bayes' equation. Bayes' equation says we start off with uncertainty, we reduce that uncertainty somewhat through a likelihood function, and there are the two receptacles for the two types of information required in hypothesis testing. It says we start off with expert knowledge, and expert knowledge is a random number generator constrained by geological knowledge. It says after we've history matched, we'll still have uncertainty, and then this is what we take to the decision-making process. So where does the calibration fit into this? The Bayes equation, the only true mathematical descriptor of what we do when we're building models and history matching. The word calibration actually does not feature in Bayes' equation, yet the deliverable is so often a calibrated model with a certain requirement for a goodness of fit. And it has no place at all in the only scientific mathematical description of the history-making process. So why do we calibrate? Partly cultural, but partly because probability distributions are just a little too hot to handle numerically. It is easier to come up with a calibrated model, but if we do, the sense of finality associated with that word calibration should disappear, because there is no sense of finality. In calibration, we pluck uniqueness out of non-uniqueness. We say there shall be one solution to an inverse problem when in fact there are a million. The only excuse for the calibrated model is if it's the first step in a two-step process of first coming up with uniqueness as a numerical convenience, and secondly using that as a starting point for quantitative error analysis as a surrogate for uncertainty analysis, which we could do but can't if we were to implement Bayes' equation. And the metric for the calibrated model can only be one: to come up with a solution to the inverse problem, which is a minimum error variance. And by that I mean roughly, so that we're making predictions roughly that our potential for wrongness is symmetrical with respect to that prediction. That way it forms the proper starting point for the second stage of the Bayesian two-step, which is the quantification of predictive error as a surrogate for quantification of predictive uncertainty. Rarely again is this ever stated in the metrics and guidelines that we normally are given to us when we're building models. So, and just to show, and I always show these slides, if you think, oh, it doesn't matter, once the model's calibrated, it can't have too much uncertainty, just to dispel any myths in that regard, it's done by a student of mine a few years ago, a rectangular grid, a particle, a stochastic field, and that's how long it takes the particle to get to the bottom of the system. We make that same prediction with a perfectly calibrated model, in this case against 12 heads, no noise associated with the data, using the finest principles of regularized inversion to calibrate that model. That's as much of the detail as I can infer from the calibration process, and in doing so I get my prediction 100% wrong. Is that it with a perfectly calibrated model? Does that mean that this model is bad? Actually no. Wrong metric again. This model is only bad, not if it gives the wrong answer, because all models are going to give the wrong answer. This model is bad if the right answer doesn't lie within the uncertainty limits as quantified by that model. If that happens, if we commit this type 2 statistical error, and then that's failure. As it stands, we can quantify the uncertainty associated with that prediction, and it does fall within the uncertainty limits using tools available in PEST. So, let's address the level of how complex the model should be, because we've now got the metrics by which to judge, start making some decisions about how we model. And one of the first decisions is always going to be simplicity versus complexity. So if I had this model here, which has got 3 parameters, the blue zone is 1 and the different shades of green are another 2, if I calibrated that, I'd get a good fit with the data. When I made my prediction and quantified uncertainty, I'd get it wrong because I'm not representing the detail on which that prediction depends. I've committed a type 2 statistical error. That's bad. However, if I didn't calibrate, if I just said I'm going to look at the best case, worst case by assigning each one of those zones the highest and lowest permeability that's compatible with the geology, I'd over-predict uncertainty. If I could reject the hypothesis of a bad thing happening on a simple model that includes the cost of simplicity in the uncertainty analysis, it is rejected, and that's as complicated as I need to be. The key here is that complexity itself doesn't do anything. We will come to that in a minute. But a simple model can often be used instead of a complex one, but only if inbuilt in the usage of the simple model is the cost of simplicity, the man-made uncertainty associated with using a simple model to represent far more complex geology and processes. Use of a simple model itself is not bad and often quite appropriate and quite financially sound, as long as the cost of simplicity is included in the uncertainty analysis so that it's demonstrably conservative and we don't commit the type 2 statistical error. So why then do we add complexity to a model? Not so that it looks good, not so that it looks like a figment of the geologist's imagination, not so that an academic reviewer will say you've got everything in it, you know, I've spent my lifetime studying and if you left out the model would be disaster. No, it's because if we're going to follow this chain of logic, that if we want to reject a hypothesis, and we can't with a simple model, then we get more complex because we may be able to reject a hypothesis that we otherwise couldn't reject. Why? Because a complex model has more receptacles for the 2 types of information that we require to reject a hypothesis: expert knowledge and historical behaviour of the system. That's why we get more complex. But then we start getting into a paradox. If that's the case, then let's look at expert knowledge. As I said before, expert knowledge is a random number generator. If we are going to express expert knowledge, then that model's got to be used together with geostatistical software or something that can express the stochastic nature of expert knowledge. If we are going to provide more parameters to do better history matching, that model's got to be used with something like PEST, which can get information out of the historical data set and into the parameters of the model. So what that means is to say that the model should be the deliverable is sort of nonsense. To say that model should be a noun and not a verb is sort of nonsense. To say that modelling should be a process, what in the hell is that? It's not here. Now, I'm completely thrown by that. Okay, modelling should be a process in which the model is just part of maybe a suite of software as complex as the model itself, with which the model dances to test and possibly reject hypotheses concerning that are salient to the decision-making process. So, again, to say then that the end product shall be the model, that doesn't make sense. The modelling, if we're going to look at it following this chain of logic that I'm trying to build, has to be a process, and the model is used in partnership with other software to test and possibly reject hypotheses of decision-making interest. But here's the great paradox. How many times have I seen models that are great, big, unwieldy, complex things, take a long time to run, numerically unstable, and the only thing that a complex model can promise, if you follow this chain of logic, is to test and reject hypotheses, but because of high run times, numerical instability, it is completely emasculated in doing the only thing it can possibly do to test and reject hypotheses because it takes too long to run. What good is this? Often I think this hampers rather than aids the decision-making process. But still, this is often the deliverable, the cumbersome deliverable that is provided and say, here, run the model, make an outcome. We've got no idea of the uncertainty associated with its predictions. So we have to make compromises, we have to make the model somewhat simple, even though we'd like to make it more complicated, because we've got to be able to use it with its partners. But then we have the problem of working with defective models. Well, actually all models are defective, but they're going to have to be defective to be practically usable. They're going to have to be somewhat simplified, but as complicated as we can make them so that they're salient to the processes on which the prediction depends. What then are the repercussions of using a defective model? And here are more decisions that the modeler has to make for which a framework is required. All models are defective, so what are the repercussions? Well, some of you have seen this. This is done by a colleague of mine in a model he was building in South Florida where he's assessing aquifer storage and recovery. And there's linear software available through the PEST suite which allows us to analyse the cost of simplicity to some extent. You've got to have a model here and a more complex model behind it. But this is a huge issue, I think. We've got to make models complex enough to be usable, simple enough to be practical, and in doing so, for the reasons I said before, include the cost of simplicity, the man-made uncertainty in the hypothesis testing, which is the role of the model in the decision-making process. Using software available in the PEST suite, we can draw graphs like this. We can say that if we don't calibrate, out on the left here, then that's the uncertainty associated with the prediction. We history match, it gets better and better. This is the point, this is the level of fit I should seek, and that's the equation used to assess that. In fact, as soon as you take defects into account, things change radically. The point at which I should fit is now back here. I shouldn't fit quite as well. But how much should I misfit? Normally I have no idea. This is something that's not even on the radar screen of most modelling exercises. It says perhaps for making certain predictions don't fit as well as you otherwise would. Here's another prediction. There's the minimum of the curve. That says that in making this prediction, for this particular prediction, any history matching of a defective model can actually incur bias that you didn't have if you weren't calibrating. So this is starting to get truly frightening. If you do the theory, and then it says that as soon as you accept the fact that a model's got defects, the link between good parameters and good predictions is broken. If a prediction is very much like what you're calibrating against, and you can calibrate the hell out of that model, and you'll get you'll get a reduced uncertainty of the prediction, even if the model is defective. If a prediction depends in a certain way on parameters, especially those that can't be estimated that lie in the null space, it could be that you can incur bias in calibrating that model because of the surrogate roles that parameters have to take to do the history matching to make up for the model defects, in which case calibrating the model can do more harm than good, or you've got a reduced level of fit. So how do we know what to do? This is something our industry has hardly even begun to address. And then we can have situations like this, where just recently this happened to me, where I said, well, this prediction I can show using linear analysis software isn't going to be reduced much by the history matching process. Let's not calibrate at all. And I say that after spending a lifetime developing software to aid in the calibration process. Instead of calibrating, let's use geostatistical methods and have the prior as a surrogate for the posterior uncertainty distribution. In which case, I'd say I'm not going to match the history exactly, I'm going to match it in a probabilistic sense while generating many realizations based on the prior only. This was rejected as a proposal because it wasn't in accordance with this dreadful document we've got at home called the Australian Groundwater Modelling Guidelines, which say thou shalt history match if thou art going to make a prediction. Yet, a little bit of maths and a lot of common sense tells you there are certain times when maybe history matching could do more harm than good. But we're not allowed to do that because we're not used to that concept, because it hasn't been looked at and certainly hasn't been included in the latest round of guidelines built by the self-appointed high priests of our industry. Self-appointed. Well, they appoint themselves as high priest, I appoint them as monkeys. So, conclusions. A lot of the current modelling paradigm that we're using has a lot of problems. The idea that one size fits all, that we can build a model, the deliverable, calibrate it and make any number of predictions, I think is not in accordance with what the decision-making process demands, not in accordance with mathematics, not in accordance with the scientific method, not in accordance with the nature of knowledge. That there will be many decisions we have to make along the road, and each one of them we've got a metric, we've got a decision we've got to make, we've got a hypothesis we need to test and possibly reject, and fitting in the history matching process, the complexity of the model, all has to be done with this prediction in mind. And when we're looking at this prediction, possibly in the same area, but of a different type, it's possible that the path we take, the model we choose, the history matching we do, how well we history match, has all got to be related to our ability to test and reject that hypothesis with a scientific instrument that is blunt, but still a scientific instrument. That modelling is a verb, not a noun. The deliverable is the process by which hypotheses are tested and possibly rejected, and that unless we sort of, even though what I've said I hope is fairly obvious, it's still not there in a lot of the guidelines we have to follow when we build models. And if we're going to build a scientific instrument rather than a crystal ball, sadly, even at this mature stage of our industry, we need to go back to first principles and ask ourselves just what we're doing, and then relate the decisions we make to those principles. And that is where I'll finish up.